Okay, so this is in principle a 2-hour session that I would like to spend in explaining a little bit what are the basics of statistics for your data analysis. This is very much from the theoretical point of view, so there is rather no connection, direct connection with the magic software, but there is a connection with the magic general features of the analysis, which are used in this theory. Well, first of all, I would like you to interrupt me whenever you have questions, because I think it's better if they are solved on the way, because otherwise, at some point you get lost, and there are a few concepts, not very difficult. Probably many of you already know them, but it's good that they are used mostly all along the talk, and it's important that you don't get missed at any point. So here is the bibliography I've been using. Basically, this Glenn and Cowan book is what I use for the unfolding part, so the last part of this talk. And then there is mostly all of the parts of the statistical concepts that are used that are taken from the particle data book, which you have the reference 2012 edition here. And also I'm using Rolke paper, Lee and Ma paper. This paper of us for the full likelihood method, and I should say that everything that I'm going to explain, apart from the unfolding, is already at the wiki. I think it's called the upper limit computation section or something like that. You can check also formulas and explanation. So this is the topics I would like to talk about. First, I will make a very extensive introduction on the basic statistical concepts. I will not go deep into statistics. I will just define and try to get clear only the concept that will be used to make then the computation of the significance of an excess detected by magic, to compute upper limits, to make the combination of results which have been taken with different telescope configurations or even different telescopes, in general, to combine with combination of results. I will spend a few minutes on the full likelihood. It's not in black, but rather in gray, because I would skip that in case there is no time, although it's the least important, let's say the least general is not used in the general magic analysis right now. So in this, because of this, I could skip it in case of need. And the last part will be about the unfolding. So the first section would be general, as I said, and the last section would be general, not connected to magic directly. And all this from 2 to 5, I will concentrate on the magic case. Okay, so first part, the introduction. Here's a list of the basic concepts I will be talking about. PDF and likelihood. This is very simple things, but that are used all the time in the rest of the talk, and then you should get acquainted with. What is a confidence interval and the associated confidence level, which we use, for example, to provide upper limits and so. The likelihood ratio test, that is a method that is used everywhere for the confidence intervals, but also to compute the significance of a detection. What is a nuisance parameter, and how do we treat it in all this framework? And the way we treat it is called the profile likelihood. We will see what it is. And finally, also I will mention a little bit methods for hypothesis test, which is also based in the likelihood ratio test. So everything is coherent in a sense. And that is used also, for example, for significance computation. So the PDF. What is a PDF? PDF stands for probability density function. And it's the function that tells us that when we are measuring an observable or a parameter, for example, the energy of an event, that we would call it theta, we have access to this parameter through an estimator that we will call x. Now the estimator is characterized by a probability density function, PDF, that I will call f of x and theta, and that function describes how the value of x distributes for a given value of theta. Okay? So imagine this case, this simple case. You have theta equal to some value, theta 0, and then the values of x that you would get from your estimator can distribute, for example, like this. This is a Gaussian with a certain width, sigma, and the difference between the value, the mean of this Gaussian and the real value of the parameter you want to measure, we call it bias, B. Okay, so this is for the case of a Gaussian PDA. It doesn't have to be like that, but it's common in experiments that you try to define estimators that look as much as this, because it has very nice properties. Now the likelihood is exactly the same function, but is the same function, but considering theta as the variable instead of the parameter and x the parameter instead of the variable. Okay. So it tells us what we learn about an observable after having measured a certain value of the estimator x. Okay. Now you can think about it as a probability, because normally we say, okay, if I measure x, the probability of theta is having this or that value. Okay, it's fine if you think it like this, but it's not like this. I mean, there is no such probability because theta is a real parameter and it has a fixed value. It doesn't have there is no probability associated to its value. The value is fixed. That's why we call it a likelihood. I mean, the statisticians they want to be very precise in what they say, and then the reason why this function is not called a probability but a likelihood is because of that. There's really not a probability. Also, it has many of the properties. Now, likelihood could look like this if everything behaves in a Gaussian way. That would be now, instead of this x-axis would be the values of the parameter of theta, and if we measure certain value x0, that could be, for example, the likelihood of theta for this x0. Now, confidence intervals. Well, normally the goal of the experiment is to determine a parameter, for example, the energy of the gamma ray, or the number of gamma rays events in a given observation. That could be observables that we want to determine. And the result is usually expressed by quoting, in addition to the parameter, to the value, to the most likely parameter, a confidence interval. And that confidence interval reflects the statistical precision of the measurement we are doing. For example, if we were measuring this, we would say, okay, theta, we are measuring theta as this value, plus or minus this, minus the bias, of course, plus or minus the width of this distribution. Now, this confidence interval would have a confidence level associated to it. Now, the confidence level is that. A method is to determine confidence intervals is said to have a confidence level given by this expression. This is just to convert a probability alpha into a percentage. So the confidence level would be times 1 minus alpha %. If we repeated the same experiment many times, the resultant intervals that we would produce by the method would include the true parameter, this quantity, this percentage of the time, no matter what the true parameter is. Okay? Now here I write at least, which in principle I think is not correct. It should be exactly that number. But this I find in many papers and literature in experimental physics, and we will see later why. Because it's very difficult to have these methods which are precisely this confidence, this probability. That the confidence level defines an exact probability and not a minimum one.
The sound is very low. Yep, better. Okay, now imagine we have this this estimator here, this likelihood, sorry, and if the likelihood had this this Gaussian shape, and we can very easily define a confidence interval which has a very exact confidence level based on the values on this table. So this is alpha, which is related to the confidence level by this formula here. So this here would correspond to 68, more or less 68% confidence level. That is 1 sigma. So we should integrate. That would mean that the confidence interval would be from -1 to 1. For 2 sigma, from -2 to 2. And it would correspond to 95, a little bit more than 95%. So this for integer number of standard deviation or sigma, we have the corresponding probability of the tails, and this would correspond to the confidence level. And here for, let's say, nice or beautiful alpha numbers, we have what is the corresponding number of sigma that we should integrate in the tails to get this the exact confidence level.
What is B?
B is the bias. Yeah, if there is no bias, it's just to get it compatible with the nomenclature that I was defining in the previous. Actually, this plot is from the particle data group, and you will see that I had to put something on top just to be using the same nomenclature. And maybe it's wrong because I did it yesterday night, but I don't think. More questions? Now, upper limits are confidence intervals which are defined from -infinity or 0 for positive defined observables up to a certain value that defines our upper limit. Okay. So this that I was showing before defines symmetrical intervals. So it has, with respect to the center, the tails that are integrated away are at the same distance from the mean value, whereas the one-sided interval, that is what normally we use for upper limits, is just integrating out the upper tail of the likelihood. And that, of course, if this is 90% confidence level, if you integrate the same portion here, it would correspond to 95% because you are removing this. You are including now this 5%, this extra 5%. Now there is a problem that in order to keep the confidence level exact, that means that when we repeat many times the experiment, the number of times that our defined confidence interval would contain the true value is exactly the number of times we have selected. One must not decide whether to provide two-sided or one-sided interval based on the result of the measurement. This is a decision that should be taken a priori. Otherwise, we lose coverage, and that means that the confidence level is not what we think it is. And this is a mistake we usually do. What do you mean by what? So you make an experiment and you say, my result will be expressed by one-sided confidence interval or two-sided. And this you keep. No matter what the result is, you keep this, because otherwise, I mean, I have not prepared a slide to show that this is the case, but it can be shown that
You mean that we have to decide whether to set an upper limit before we know whether we have to set
yes,
an upper limit?
yes. Well, I mean, there are methods that are in this case are dynamic in the sense that they provide, like Rolke does this. It provides upper confidence level, which in principle is two-sided, but one of the sides can be the boundary of the physical region. For example, in the case of the number of gamma rays, it's 0, okay, and then it becomes like a one-sided, but it's two-sided. And they try to keep coverage, but we will see that, I mean, this introduces additional problems, and it's very difficult to keep coverage. So at the end, I think we have to accept that coverage will not be exact, and that's it. We have to know about that. Yes?
Can an upper limit be two-sided?
No, an upper limit is just this case.
Would you say there we have to decide whether one or two-sided interval?
Yes.
What?
I mean, from statistical point of view, you can decide this and that, and you will get a result. Okay.
But the one is a lower limit, and the one. No, the one is.
For you, the problem is that this lower limit could be, for example, in the case of gamma, of the intensity of gamma rays, it could be a negative value.
Then discard it.
Then
we need to get rid of it. It's always.
Okay, this is the physics point of view, but it's not the statistics point of view. From statistics point of view, this value would be completely valid. No problem with that, because the only property that the interval that you define has to fulfill is that it contains the real value in a certain percentage of the experiments. So the rest of the experiments, for example, if you define 95% confidence level, 5% of the times that you do an experiment, your interval will not contain the real value. And that can be, for example, that in the case of a positively defined quantity, you get a two-sided interval which is completely negative. Okay, from statistics point of view, there is no problem. This, you know for sure, does not contain the real value, but statistically speaking, is correct, because you are allowed to get this kind of result 5% of the times for 95% confidence level intervals. Okay. I will come to that later when I talk about Rolke. Okay, I think this request that you get results which are in the physical region is a request from the physicist, and it's normal that we do that. And it introduces problems. And the main one that introduces is that the coverage is not fulfilled. Okay, so this property that your interval contains the right result in a certain percentage of the times is not fulfilled anymore. Now, in this case, that's why I was saying before, at least, because in this case, what you do is normally use methods that produce over coverage. They contain the right result more times than this 95%, but not less.
Can we include in the statistics?
We do it, but at the cost of losing coverage. It's, as far as I know, there is no way to do it in the. Yes.
How is coverage defined?
Okay, coverage. The property of coverage is that if you say that your method produces a confidence interval with a certain confidence level, this confidence level is exact. That means it will, when you repeat the experiment so many times, this for example, 95% confidence level, 95% of the times, your interval will contain the right result. If that property is fulfilled, then it is said, it's just an expression, it is said that you have coverage, the right coverage if you want. If it is not fulfilled, you can have under coverage or over coverage. Over coverage is that you contain the real value more times that you specified. So for 95%, and you include if you have over coverage, that means that your interval will contain 96, 97, 98% of the times the good result. Under coverage would be 92, 90, whatever, less than 95. Is what? It's a statement about the confidence interval, your method of defining confidence intervals. If the method you use as a result produces confidence interval with this property, exactly, you have coverage. If it doesn't, you don't. And it can be conservative, let's say, if you have over coverage, or dangerous if you have under coverage.
How do you check this? How do you check this?
Normally with simulations. I mean, sometimes by construction you are sure that that is like that. If you were if you know your likelihood, and you don't do any tricks. I mean, for example, you allow results with any sign. You don't care if you have negative signs, then you are sure. Normally, it's not like that because the likelihood is not precisely known at the maximum, and then in order to be sure, you always make simulations and see what you get, because you can fake these experiments and repeat it many times and see how many times you get the interval containing the right value in your simulation.
So in the last point of the slide, so you're saying that in principle, once we make a matching, we should not decide whether to make the upper limit or to compute the error bars for the estimated flux, for example.
If you want to keep coverage, let's put it in another way. When you decide whether to provide to provide an upper limit or a double-sided interval based on your result, you lose coverage. Okay, I think this is something we do normally, and for me the point is to make you know that this is making the nice statistical property of this method is lost. Let me go further, because later I will explain Rolke and how Rolke treats this thing, and you will see what happens, okay? But good that you're making questions. So now the likelihood ratio test that we will use for many things. This is, in principle, in this context, is a method for constructing confidence interval, and it's based on this so-called likelihood ratio test statistics lambda, and that is given by this expression here. So this is the ratio between two likelihoods. Well, it's the same likelihood, but in the numerator we have it evaluated at the point theta prime where the likelihood is maximized, and here is evaluated at the value of theta, which is our variable in this context. Okay, so theta prime, okay, are the values, can be multidimensional. Okay, so this works whether theta is a single parameter or many parameters, and the same for the data. X here is the measurements. Okay, so we are evaluating the likelihood of the parameter, for example, the number of gamma rays, when we are measuring some x that can be, in our case, n off and on, number of on events, number of off events. So this can be maximized, like in the numerator. In the denominator is free. Now this, in the case of big numbers, let's say, in the limit of big numbers, has the useful property, this likelihood ratio test, that if you take the log and then put -2 on before, it behaves as a chi-square. Chi-square of m degrees of freedom. M would be the size of the vector of the number of the free parameters theta. Okay. So, for example, if we want to estimate the number of gamma rays, m is 1, and it's just a chi-square with 1 degree of freedom. So the limits with a certain confidence interval, with a certain confidence level interval, are defined by the values of theta below and above this, the one that provides the minimum of this -2 log lambda, such that they reach the percentile of the chi-square distribution with m degrees of freedom, as we were showing before. So, for example, this would be for a normal case or a nice case, let's say, the shape of the -2 the log of the likelihood ratio. It will look like a parabola. It will have a minimum. The minimum, the value of theta where this function reaches the minimum would be the one that provides the best fit, let's say, and then we can go below and above and see where this theta where this function crosses a certain value, and this certain value tells us what is the confidence interval, the confidence level that we are imposing. So this is a list for given values of the confidence level so 68.3%, 95%, etc. What would be for 1 degree of freedom? That would be different for several degrees of freedom. Okay, this table you can find in the particle data group, also for M2 and for M3, and you can find its values tabulated in many places. So, for example, we have to find 95% confidence interval. Then we go to the minimum, we go and check where this function crosses this value, 3.84, and this would produce the boundaries of our 95% symmetric confidence interval. Questions?
Why is it symmetric?
Who said that?
Chi-square distribution symmetric?
The chi-square distribution, well, this is not the chi-square distribution, okay? This is this is this function here. It distributes, huh?
You said it's chi-square distributed.
Yeah, but that doesn't mean that the value with respect of theta has a shape of a chi-square distribution. This is how a chi-square function looks like. Another thing is how let's say, if this is a true value and we would be making an experiment, the values of this, the values of the function that we will get for the minimum of theta, those would distribute like a chi-square distribution. But this is the same shape of, this function has the same shape than when you do a chi-square test, a least square test, for example, you would get this the same shape. It's the same function, if you will, except you can move it. I mean, this is by construction. It always has a minimum at 0 because of the way we have constructed.
It can be asymmetric.
Yeah, that depends on the estimate, on the likelihood. Yes. This is for a Gaussian, everything is Gaussian. If all the estimators of the likelihoods are Gaussian, you will get something like this. If not, depending on the PDFs of your estimators and therefore on the likelihood, this can be asymmetric. This can have very nasty shapes that don't allow this kind of minimization or definition of the intervals. Yeah, Belardo.
The number M there, the number of degrees of freedom,
Yes.
Is equal to the difference in the number of degrees of freedom of the two hypotheses of test.
This is not a hypothesis test right now.
Okay.
This would be since this is all fixed, let's say, because this is the minimum, is the number of parameters, of free parameters.
So this is the ratio just to the minimum.
Yes.
Okay.
Yes. That's why this is 0 by definition. The minimum has to be a 0. Now, what happens if we have nuisance parameters? And first of all, what are nuisance parameters? Well, those are parameters which affect our measurement, but in principle, we are not interested in determining, okay? For example, in the magic case, we have the number of background events. Number of background events is something which is affecting very much our measurement, but we don't care what the value is. We care because we want to extract the number of gamma ray events, okay? But not because we are really interested. We could, but we are not. In this sense, when you construct a likelihood, you construct with all the parameters which are relevant, and then you can treat one or the other as nuisance at your wish. So maybe for different problems, a parameter can be a relevant one or a nuisance one. In the case of magic, it's more or less, at least for standard analysis, it's always the same. Number of gamma ray events is the parameter we want to estimate, and the number of background events is a nuisance parameter. There are more. Now, what happens in this case? Well, we can include them. They will be by construction included in our likelihood. So what we do is to distinguish in this likelihood ratio. Now I put a P now because when we have nuisance parameters, the likelihood ratio is called profile likelihood. And now this is the likelihood at the value of the likelihood for the values of theta and nu, which maximize the likelihood. Okay, so that's a number. That's not a function. And this is the value. This is the likelihood evaluated for the nu that maximizes for a given theta and maximizes the likelihood. Okay? So this and this don't have to be the same because that produces the absolute minimum of the likelihood. So this value here and this nu star would be for each of the values along this line, nu will be chosen in order to maximize this likelihood here. So the presence of nuisance parameters with respect to the case where we don't or we fix them, what the effect it makes is to widen this minus 2 log lambda, and then it widens correspondingly the size of the confidence interval. But they have the same in principle. Well, it's not completely exactly true, but in principle it has this profile likelihood has the same property of behaving as a chi-square distribution as the normal likelihood ratio, and we assume it does because for many practical cases it's a good approximation. Now let's move to yes,
This
please.
method still is keeping this chi-square distribution of lambda.
Say it again.
It seems rather arbitrary. Just taking the maximum. This 2 log lambda p still
Yes.
chi-square distribution.
Yes. As I was saying, is well. I think mathematically is not completely correct, but for many cases, probably depends on how the distribution or the likelihood for the nuisance parameter is. But if you consider this as because this enters the composite likelihood as normally as a Gaussian term. If the uncertainty that we allow on these parameters is Gaussian, for example, and in this case, for example, it fulfills the profile likelihood fulfills the same property as the normal one. Yes.
So in this case, is there in the minimum both the estimator and the nuisance parameters are the same?
Say it again.
That in the minimum, where both parameters meet?
Yeah, this minimum doesn't have to be in the same position actually. Yes, this green curve could be shifted to one side or the other because the minimum of this function here, I mean the value of theta, which is this axis here, that minimizes maximizes the likelihood. If you have a nuisance parameter, it doesn't have to be the same as in the case where there is no nuisance parameter. So these two parabolas could be shifted.
But in any case, the profile likelihood in the minimum, both the observable and the nuisance parameters are exactly the same. But when you try to move away from the minimum, then
Exactly the same. You mean zero? This is by construction.
I mean that the upper part of the ratio is theta prime nu prime, and those parameters are the ones that maximize the likelihood, right?
Yes.
And then in the denominator, where okay, the minimum.
Okay. Now something a bit different but related is hypothesis test. So what is a hypothesis? Okay, let's consider an experiment whose outcome is characterized by a vector of data x. For example, an off and on. Okay. So a hypothesis is a statement about the distribution of this x. How this, what is the PDF of this x? For example, it could define completely the PDF for the data, a simple hypothesis. An example of this would be there is no gamma ray events in my own sample because we are saying that the PDF should be that for the expected value equal to 0, okay? Or it could specify only the functional form of the PDF, letting some free parameters, and that in that case we call it composite hypothesis. For example, the spectrum of the gamma ray events on my own sample is a power law. We don't say which power law, we say it's a power law. That's another hypothesis. And these are things that we can test with the hypothesis test. Now, hypothesis test is a rule that states for which values of the data X a given hypothesis, often called the null hypothesis and represented by H0, should be rejected. Now, this is done by defining a critical region in the X space. For example, in the case of two-dimensional data, X1 and X2, we could define a region such that if the hypothesis is true, there is less than a certain probability that we call alpha, and it's called significance level of the test, to find the values of X in such region. In other words, if the data are in the critical region, H0 is rejected. We have this map here. This is our critical region because we have computed that the probability of getting our result in this region is less than 5%. In case our hypothesis is true, then if we measure something in this region, we would be rejecting to this confidence level, 95%, the hypothesis. Okay. Now there is a problem with this definition because normally there are infinite number of ways to define the critical region with a certain probability. Because in this, if we go back to this map, well, you can modify this line entering here but compensating with some other region there so that the probability stays the same. Okay? So there is, normally what is done is to compare the probabilities for the data predicted by some other alternative hypothesis H1. Now, the Niemann-Persson lemma says that the optimal test of H0 with respect to alternative H1, and optimal means that, let's say, if separates the most H1 and H0, so if H1 is true, that would be rejected. Well, that optimal test is such that the critical region is defined by the likelihood ratio test. Again, the likelihood ratio, as we see. The likelihood ratio for a hypothesis, for the new hypothesis, and given the data x, would look like this. On the numerator, we have the likelihood of the alternative hypothesis given the same data, and the denominator, the likelihood of the null hypothesis.
H0 is the teaser power law or the teaser power law? Your example.
H0 can be whatever you want. It's the one you want to test. Okay. Normally, H0, for example, a very practical example in magic is H0 is there is no gamma rays in my own sample. This would be my null hypothesis. Now, if you are able to reject that hypothesis, it means that there is gamma rays. Okay. And this is the use I will make of this hypothesis test actually. So now, sometimes we want to compare a given hypothesis with a set of alternative hypotheses, okay? And then in order to do this, we have to parameterize the set of hypotheses by a set of parameters, again, theta, and then H0, the null hypothesis, is given by a certain value of the data, okay? Theta equal to theta 0, for example. Number of gamma ray events equals 0. That would be my null hypothesis. And then any other value of theta is H1, whatever it is. Now, then we can define a critical region using the maximum likelihood ratio, again, which is given by this expression that now looks exactly the same as for the case of defining confidence intervals, okay? So that would be the test for a given theta 0 with respect, and this would be the value that maximizes the likelihood. So we are comparing the case where in the case of number of gamma ray events, theta being the number of gamma ray events, we will be comparing the case where this number is 0 with the case whatever other case that maximizes the likelihood, okay? And then again, we have this property that we use. For example, if m equal 1, we have only one parameter, like the case of the example in following. The critical region to reject theta 0, so no gamma rays, with a significance, let's say, of 3 sigma, is given by those values of x for which this property is fulfilled. So the square root of the -2 log the likelihood ratio is greater than 3. This 3 is just the number of standard deviations by construction, okay, because of this property here. Now, that was all for the introduction of the basic concepts. Now I will concentrate on how all these apply to my. I have been trying to provide examples of magic analysis, but now I will be going more in depth in that. Well, how long is it?
30 minutes before the coffee break.
So I have been talking for 30 minutes now? Or, okay. 40, okay. So first, what is the likelihood at work in magic? And I'm talking about the basic analysis. So when we want to see in our theta square plot whether we have a significant signal or not. Well, the relevant variables here are n on, which is the number of events measured in the signal region. This is an integer number and a random number. N off is the same for the off region. Let me call G the estimated number of signal, in this case gamma ray events, in the on region. This is an unknown. And B the estimated number of background events in the on region. Okay. Now tau will be the ratio between the off and on exposures. Now n on and n off are random variables which follow Poisson statistics, okay? And the joint likelihood then for the number of gamma ray events and background events is given by the product of these two Poisson. This is the regular Poisson formula. This would be the term corresponding to the on, and this would be the term corresponding to the off. So in the on we have gammas and background, and this is our measurement. And in the off we have tau times the number of backgrounds, because tau is the number of, let's say the number of off regions could be tau, for example. And we measure n off. And this is the composite likelihood. Here I am assuming that tau is perfectly known. This is not exactly true, but is, for the sake of simplicity, is useful to consider it here. So now, let's make a hypothesis about G, and let's keep in mind that B, which is the number of background events in our own sample, is a nuisance parameter. So now we accept or reject hypothesis with the profile likelihood ratio, as we have seen before. And for the magic case, now the parameter we want to determine is G, number of gamma ray events. These are our data. So now this is how this latent ratio would look like, including B as a nuisance parameter. Now in gamma ray astronomy, normally the threshold for rejecting the hypothesis that there is no gamma ray is set by this value. So the square root of the -2 log of the likelihood ratio, of the profile likelihood ratio, is equal to 5. That's having 5 sigma in your data. That's how we say it. And in general, we can compute the significance of a detection, and the probability content of this G equals 0, given the measured n on and n off. So the significance would be the square root of the -2 log the profile likelihood ratio evaluated at G equals 0, given the data. Now, for this ideal likelihood, you can compute these values, G prime, B prime, and B star, analytically, okay? Actually, G prime and B prime are straightforward, so the number of gamma rays is estimated as n on minus n background. This would be the normalized n off, if you will. And the number of background is the usual expression. Now, for a given g, if you take a value of g and differentiate the formula for the likelihood for b and make it equal to 0, then you can extract the value for b star given a g, okay, given a number of gamma ray events, and it looks like this. It's tedious to get, but it's easy, relatively easy. Now you can use these values, these three values, you can introduce them in your profile likelihood here, and then compute this square root here, evaluated at g equals 0. Everything is known in this formula.
How do you get this done? How do you calculate
B star, okay, you take the likelihood here, and you make the derivative of, you fix g is a fixed number, and you take you differentiate against b. Make it equal to 0 to get the maximum, to maximize for b, and then you get this. As I said, this is something you can do. You can differentiate this formula, and you do it with care, because it's a big formula and it's tedious, but it's trivial to do it, let's say. Now you introduce all these values into the formula of the likelihood of the profile likelihood ratio. Take the -2 log and the square root, and that's the definition of significance. Okay, and when you do so using these values, then you get for the significance this formula, and this formula is Lima formula number 70.
analytical? It can also be numerical.
This is completely analytical.
Here. But in general,
No, in general, it depends on the likelihood. As soon as you include in Roque is explained for several complications that he adds, because Roque, you know, that adds an additional component. I think I will show it later. Yeah, this is Roque. Roque is the n-on Poisson, n-off Poisson, and this is a Gaussian for this efficiency of the cuts, let's say. I think this is not solvable, but I'm not sure. I mean, because it could be. It's written in Roque paper. You can find for several examples, but in general, it depends on the expression of the likelihood. Okay. Also, the number of free parameters, because if you include the nuisance parameters, you have to differentiate against them too. And then you have a system of equations, and when you have more equations, the probability, let's say, it's less likely that you get an analytical solution. Okay, so this was all about significance. Now let me move back to upper limits. Sure.
Value if we have very large count numbers, because only then our Poisson distribution will approximate the Gaussian. So what happens if we don't have them? I mean, then the estimated significance value will not correspond to the sigma value.
That's true. Yes. And actually, I think we have this problem.
This value or this limit of 5 will not make any sense.
Yes, but this is, I mean, for the normal detection, let's say, this is not our problem, because we have normally huge statistics. This problem happens normally in the real analysis, and maybe Julian can correct me. When you do sky plots, because at the borders of the sky plots, you start having very low statistics, and then you can see why you get all these, very bright colors and very dark, because the fluctuations there they are out of control. But this is not. This problem is not well treated in magic, I would say, because it's not worth, because it's not our main problem. Normally we have lots of background events, and then it's guaranteed that this significance is correctly computed. Now let's start for the upper limit calculation. Let's start again with the ideal on-off, purely on-off Poisson likelihood. So Poisson for on, Poisson for off. We construct the profile likelihood ratio as usual, and then we solve the equation for G. Okay, -2 log the profile likelihood is equal to a certain value. Okay. This equation, by the way, is also solvable analytically for this Poisson. Now, the values of G that solve this equation would provide us with a 95%, with a certain confidence level interval, depending on this value. For example, for 95% one-sided interval, this value delta log of likelihood ratio would be 2.71, and this you can get from the table that I showed already in slide number 10. Okay, so if you know the confidence level, then you can go to the tables and find your delta log. You plug it into this equation, and then you can find the values of G that solve the equation, and this provides you with your interval. Now, Rolke, what does Rolke do? Well, in magic, we don't use this for upper limits. Okay, we don't use this ideal likelihood. We do it for the computation of significance, as we saw, but not for the upper limits. Why? Because we somehow include the effect of a 30% uncertainty in the efficiency of CATs, and this efficiency I call it epsilon here, and this epsilon is included as a nuisance parameter. Okay. So since this is an efficiency of gamma ray detection, it has to multiply the number of gamma rays. Yes. And then you have also the background, and this is what you measure, N on. It doesn't affect the N off, the off part, because there you don't have gamma rays. And then this is the PDF for this epsilon. This is somehow this is an assumption. We assume that that this efficiency distributes as a Gaussian, and that the mean value is 1. So in principle, what we think is our efficiency in detecting gamma ray is the central value, and it has an uncertainty of 30%. This is a decision that was taken, I don't know when, and it has been kept in magic since forever. Now, what Rolke does, the Rolke method does, is just solving this equation. So it's the likelihood profile ratio, where you have two nuisance parameters, number of background events and efficiency of the CATs, and you have two measurements, N on and N off. And then this delta log depends on the confidence level that you have to provide the method as an input. Sure.
Why do we do this efficiency only for gamma rays and not also for hadrons?
Because it doesn't make any sense to make it for the hadrons.
Does it make sense at all?
I mean, you don't care what you could plug another efficiency to B, but it will be an extra nuisance parameter that would be 100% correlated with B. There is no way to disentangle in this formula. Imagine you include a epsilon prime here, and then you include it here. There is no way to disentangle this the effect of this epsilon prime and B, because they are multiplicative. They are multiplying each other in each term. So
There is already same for E.
No, because because
No, because B is a nuisance parameter and D is not.
yes,
What's
you
the
want.
difference between nuisance parameters? I mean, we measure background and we measure signal.
No, but it's if you were interested in determining B, because it's not a nuisance parameter, then you would be right. I think Abelardo got it correct. If you were interested in determining B, you're right. But we are not. So then we don't include an extra nuisance parameter. We don't care what B is. You could do it, but
So we just add something like 30% systematic uncertainty on G.
Yes.
Just
I would rather wonder why 30%, where this 30% is coming from.
we just make our limits for this.
Perfect. This 30% I think is coming from the spectral slope, because when you take this energy scale and you assume that you have a spectrum of 2.6 or whatever, it actually becomes a very scary number. So this 30% is not that.
Well, we usually also provide limits for different assumptions on that spectrum. So it's very our you think that you translate in terms of the energy
But
This is the spectrum. This is.
Yeah, I don't see this.
For a difference.
This is global efficiency. It does not depend on the energy. So I don't see how this effect could be included through this parameter.
The point is that if you have a bias in the energy, let's say constant bias of 10%, and you have a spectrum which is 2.6, then the number of events in here, let's say you are in here in the spectrum,
Yes.
and you think that you have so many events, but in reality you are in here. You are
Yes.
10% further away in energy. And you take this 10%, 2.6 spectrum, and you end up with something which is close to this 20%. It's different for everything.
Obviously, this is a kind of a chapuza because it's not mathematically, it's not exactly what you're describing right now. So probably there are better ways, but I think it's a way to say, okay, we don't know this thing perfectly, and then we introduce some.
Yeah. And about what Max was telling before with efficiency of the background, what you're implementing here is a kind of observation-dependent efficiency. So the assumption here is that the V in both the background term and the sigma term is the same. But in reality, there is some difference.
Yes.
What we normally do is that this 30% it includes this. But it's not a very straightforward thing because it's not scaling with the strength of the source, it scales with the number of background. So if one would don't use the same B, but in one case you have B and another you have V plus this.
No, b times something. Then it would make sense. Then it would make sense. Yes, because it would take into account the fact that this b here and this b here, they don't have to be exactly the same. This would be taking into account the systematics on the background evaluation. Yes.
But this is covered.
Probably this is better than this epsilon that we are introducing. We just fall in Rolke, and this is what Rolke does. Rolke doesn't do the other thing. Let's say.
So Rolke adds this.
This is Rolke. This is
second nuisance parameter.
yes. There are several. Well, Rolke has this, but well, the background can be Gaussian or Poisson. I think we actually use the Gaussian approximation. And this PDF can also be several things. Can be Gaussian, can be binomial, can be Poisson. So it gives you some fixed examples, and you have to choose out of them which is the one that fits better your experiment. For my discussion here, it really doesn't matter. Whatever the likelihood is, the only point I want to make is that the main difference with respect to the ideal case is introducing this extra nuisance parameter, which I don't think it fits very well with magic, but somehow we use it to include some effect of systematics. Anyway, let me continue. Now, okay, as I said, what Rolke does takes this likelihood or similar and solves this equation, the usual equation, to define two-sided confidence intervals, okay? So the solutions of this equation, it will be two solutions because this is a parabola. There is G low for the lower limit, G up for the upper limit. In addition to that, it provides a prescription to what doing in the case of small or negative value of G prime. So what we were discussing at the beginning, what happens when you go outside the physical region. And let me insist on that. What happens again if the G maximizing the likelihood, or even worse, the whole confidence interval lies outside the physical region. For example, the G, these are, in this case, it means that they are negative. The statistician view, from the statistician view, there is no problem whatsoever. I mean, this is one of the cases, these alpha % cases, when your interval does not contain the resolution. You know it, but it's okay. You have to keep it in order to keep the coverage. The physicist view, our view, is saying that's stupid and it's not a result we can publish. So you should do something about it, and we do it. But then keep in mind that following this physicist view forces to take ad hoc solution for those cases, those limits close to the physics boundary, and normally involve that the nice statistical features that this method has are lost, simply. Now, what Rolke does? You will see what kind of tricks Rolke does. It's really funny. So Rolke says, okay, I'm going to produce confidence intervals always in the physical region. So that means G equal or greater than 0. Now, if G low is negative, like in this case, this is 0. This is the point where G is equal 0. So now, G low is negative, and G prime can be negative or positive, it doesn't matter. But G up is positive. What it does is say, okay, I move G low to 0, and that's it. Okay, and G up, since it's positive, I keep it. Okay, what happens if also G up is negative? Now the 0 is here. You have, if you make this profile likelihood ratio, the -2 log, then you get G low and G up in the negative. Again, G low is moved to 0. And for G up, what it does is increasing N on by units by 1 all the time until it finds the first G up, which is positive, and it keeps it. So you see how ad hoc is this procedure. And this produces over coverage. I mean, clearly, it cannot be otherwise. So that's in that sense, over coverage is better than under coverage, and then we're fine with that. But it produces large over coverage. So you can go from 90% to 95% very easily. And these are in the Rolke paper. You can find plots where you see for different configurations what are the kind of coverage, over coverage that you get.
Cannot this over coverage be corrected by applying non-symmetric boundaries?
What do you mean non-symmetric?
You have to shift this guy in here, but then the up you can play a bit.
You will always, you are artificially enlarging the intervals, okay? Because moving this, for example, in this case, it's like covering all the negative part plus whatever you have moved from G up until it gets positive. So it's larger than it should. So it will, by definition, by construction, produce over coverage. I don't see a way how this can be fixed. If you can think about it, I think it's publishable, because I don't think there is any method in the market that for such kind of likelihood produces the right coverage. So that's something to think about, because maybe it's an interesting problem from the statistical, well, not only statistical, but physics-related statistical. Now, the other thing that Rolke does, and this is related to one question that was posed before, is when n on and or n off is equal to 0, this likelihood, then this function has no minimum, okay? And then the limits are obtained by linear extrapolation of the cases, of the closest cases, let's say n on equals 1 and 2, and n off equals 1 and 2. Very ad hoc, too. Well, Rolke also, in this case here, where for the definition of the limits, it offers another possibility that I don't think we are using, is to say that we don't consider at all any value outside of the physical region. So the minimum, for example, in this case, when you are getting the absolute minimum negative, Rolke's, this other method would take this value as the minimum, because it's the minimum in the physical region, and then compute this delta log gamma lambda with respect to this value. So it would compute this 9 with respect to 15. So it would go up to 24. This is another possibility. But it produces over coverage too.
But
Okay?
in Mars, I think we are using the bounded, not the unbounded.
Do you think so? Okay, maybe.
It's not left.
I don't think so, eh? Because no, it's impossible because you get. Is it possible? Well, I don't know. I think we are by default we are using the unbounded. Yes, we use the bounded in the Sewe paper because this trick for the full likelihood, this trick of adding one event is not possible anymore because you would have to add one event with a certain energy, and then you don't know which energy to assign, and then we was somehow forced to use that. Combination of results. So what happens if you have multiple data samples which have been taken with different instruments or instruments characterized by different response functions. So the nomenclature I'll be using, well, the same and on and off G, B, and tau is the usual, but now I will be adding this subindex I to refer to the ith sample, and then I will be using also the fact that the effective area is different for the different samples. The energy and the angular resolution may also be different, but this will be somehow included in the effective area in this development. 5 minutes? Good. Now, what we want to do, or what we may want to do, is to compute confidence interval for the average gamma ray flux. It only makes sense for average, because if it's time dependent, you will be doing time bins, and for each time bin there will be one probably sample which is relevant, and then you compute it, and that's it. But if you want to merge everything together and compute confidence intervals for the average gamma ray flux, you have to make some tricks. Now, I will be assuming that everything is described now by the ideal likelihood, so Poisson for on, Poisson for off, okay? But this is just for the sake of simplicity, but you can generalize what I'm going to see very trivially to any other likelihood at work. So the way I see, there are two solutions to that problem. The first one consists on making an average likelihood. Now this average likelihood would have the same shape, so the ideal one, Poisson for on, Poisson for off. And now this total number of gamma rays would be the sum of the number of gamma rays for each individual sample. The same for the number of background events. The same for on events and off events. All the number of events are adding up. Now the only thing you have to take with a bit of care is how you compute the tau, because the tau has a rather more complicated formula, although simple enough. And then you proceed as usual. Okay, you plug all these values into your likelihood and compute the. Well, you can compute the value of G. Actually, this doesn't make much sense. And then, if you want to convert the value of G, the total number of gamma rays, into a upper limit in the flux, then you have to know that the total effective time will be the sum of the effective times for each subsample, and that the effective area is the average effective area weighted by the observation time for each of the samples. So this is taking averages everywhere. Okay. This actually here, I should remove it, because this GRB you are estimating from this formula, so it doesn't make. You are not computing each of them individually. Okay.
All the likelihoods for the individual.
That's the second option.
Oh.
I think Daniel. No, but I wanted to ask you. This is what is done in the code, I think, right? So when you have different samples, you sum all the events and then use an effective area which is with. Huh? Are there more than one code? Combining data taken by different for anything. during the unfolding.
There is no universal code for making a spectrum.
Ah.
Yes. I mean, as far as I know, maybe someone has some private copy.
No, but at some point when you want to combine the data for anything.
Yeah, it's done on the unfolding.
Yeah, but how do you do it? You do it like this or not? You don't know.
Changing the code right now.
Ah, okay. So you do it in a dynamic way. Okay, so second solution.
So let's discuss it later.
Well, the second solution is
But, sorry, can I ask you? This can be done only in the full energy range.
no why. These things
Because if you
These things you can compute in any energy range that you want, this N on and N off, and then you will be getting the corresponding number of gamma rays and backgrounds in that energy range, estimated energy range.
But you have different samples with different characteristics, different energy resolution, the effective area.
Yeah, what question? Okay, then you should go to the second solution. So now, the second solution, which I think is more exact because it doesn't take any average, is to write down the global likelihood as the product of the individual likelihoods, as you were suggesting, right? So this is, now the likelihood will have, I will explain later that the free parameter cannot be the number of gamma rays. It has to be something which is common to all the samples. And this is, for example, a flux, the gamma ray flux, the average that you are trying to measure or put a limit to. It will have contain all these nuisance parameters, B1, B blah blah, B until Bn. N is the number of samples we have. And it will contain, it will use all these data, N off for the first sample, N off for the first sample, and so on to the nth sample, okay? And now the likelihood will be the product of all these Poisson for on for the different samples, Poissons for all for the different samples. Now you have to compute. I mean, since you want to measure a single parameter or put a limit to a single parameter, this single parameter has to be used in order to compute the expected number of gamma rays in each of the sample. Okay? Because if you included G1 until Gn, you will be, and you will maximizing for them, you will be assuming that all these G's are independent, and they are not, because all the G's are coming from a single physical process, which is what you are trying to measure, right? And this is what you introduce in your likelihood, the value of the physical quantity you want to determine. And from this physical quantity, you can determine the values of the number of gamma rays in each of the individual samples. For example, if we are computing upper limit to the integral flux, okay, so then this is the integral flux, the value of G corresponding to that integral flux would be given by this expression. And this probably will be explained, where this expression is coming from will be explained by Abelardo, I guess, or I don't know. But this is the common relation between flux and number of gamma rays, effective areas, etc. Now in this formula, this E with no addition is the true energy. This is estimated energy, and this would be the spectral shape defined in this way. So the differential spectrum is given by some constant times this shape. Now, in principle, this solution should be better than the other one, because as I said, you include all the information you have. You separate, you don't make an average. When you average, you are always losing information, this you know. And then all the details for the different samples are included in the proper way. So this is, in my opinion, this is what it should be done. But it's not clear what is done. I close here, right? Okay, so break. Okay, so let me spend a couple of minutes about full likelihood. So this is a method by which, in the case we are looking for very specific spectral shape that we can know in advance, we include it in the likelihood. So we consider the spectral shape as a PDF of a random variable, which would be the estimated energy. And this information, which is normally not included in the ideal likelihood, because there you are integrating a number of events in a certain energy range. By including this extra information, you can gain sensitivity. But the condition, as I say, is that the spectral shape, this I will call S, is known. And this is not true for many cases. When you are looking for a source that you don't know what spectrum it has, well, you cannot include it. This we used for dark matter searches because there you can use models to predict the spectrum, and then you can include that prediction into your likelihood. That then it would look like this. Again, you will have a free parameter that I call theta that is related with the intensity of the signal you're looking for. And then you have a nuisance parameter, is the total number of estimated observed events. And then you have as data the individual energies that are measured for all the events in the on and off regions that you are measuring. And then the total number of events. The total number of events is just kind of a normalization factor, which is a Poisson also. And it has to be included in order to, let's say, to regularize this part here, because otherwise there are effects here that can be compensated by adding or removing number of events. But this quantity must be constrained by this Poisson. And then this second part, which is new with respect to the ideal likelihood, it's the product of the PDF of all the measured energies given the spectral shape and the intensity. So what we are doing here, instead of comparing number of events in the on and off regions, what we are doing is comparing the measured spectral shapes in the on and off regions, like it is shown in this example here. This full likelihood would be comparing this red line with the red dots, one by one, and this would be on, and this the yellow one would be off. Whereas in the likelihood, in the ideal likelihood, we are, or the conventional likelihood, we are comparing this integrated number of events, these lines here for the on and for the on, with the measurements which are represented by dots. Now the improvement in the sensitivity that you can get using this method depends on the spectral features of the on with respect to the off. So if the on and off, they have the same power law spectrum, or whatever the shape, they are the same, your gain is zero. You don't gain anything. And the more different they are, the more you gain. This gain factor of more or less 2 for the most practical cases in dark matter searches. So it was actually worth it. Now some details here of how do you write down this PDF for the energies of the different events. It's just the normalized differential rate. So the differential rate is this P with different letter than this one. This P would be this one here, not this one. This is the normalized one, and you normalize by just taking the rate and dividing it by the integral between your energy range. And of course, this rate for the off is measured directly from the data, as usual. And for the on, you have to take into account that you have a component of background, which would be the same. In principle, we are assuming that it has the same PDF, the same shape, with a normalization factor given by the number of regions you are using. And this second part takes the spectral shape convoluted with the energy dispersion function and multiplied by the effective area. And that's it. That's everything I want to say about this method. If you want to know details, there is a paper, and you can find it. Okay, I don't know if there are questions about this or any or what I said up to now. Otherwise, I will move into, in principle, a completely different topic, which is unfolding. And again, this will be very general discussion about the problem of unfolding. with not many details, just basic stuff, just to understand what the problem is, what the solutions that we have to provide are, and why. And no, I will not say anything about the actual implementation in Magic, for which I think there is a presentation, or maybe a couple of them even. So this will be the little bit the summary of this part of the lecture. So first I will describe the problem. I will provide the nomenclature in order to provide the language in which this problem is described. Then I will go to the direct solution, which is actually not a valid solution, and we will see why. And then, since this is not valid as a practical solution, then we have to find another way. And I will describe forward unfolding, which is one of the practical solutions, and the more general one, which is what is more generally known as unfolding, which is provided by adding a regularization to the problem. So what we have, well, let's assume that we want to estimate the values of a given distribution or a PDF, which I call f true, of a given random variable, which I call y. This y can be the real energy, and we want to estimate the PDF, and the PDF could be the energy spectrum, the real one of a source. Now, we don't have direct access to that, but instead we have some estimator, x, and this estimator, with this estimator we measure the distribution, and it's affected by the instrument, what is provided by the instrument. And the estimator, in general, we have a certain bias and a certain variance. So, for example, if this would be the true distribution we are trying to measure, and we are measuring it with an instrument that provides us with no bias and a resolution of 10 in these units here, these arbitrary units, 10 fixed all along the axis, this would be a possible outcome of a real measurement. So you see how this distribution is distorted because the peaks are widened, but also you see the effect of statistical fluctuation, because since this distribution is symmetric with respect to the center, and also the estimator is symmetric, is the same in the whole x-axis, the action of the estimator would provide also a symmetric distribution. The fact that this is not symmetric is because on top of that there are statistical fluctuations from a real measurement. Okay, and this is the key issue. This is why this is a problem difficult to solve or interesting to solve, is the combination of these two effects: purely statistical random fluctuations and the limited resolution of the instrument. Now, the procedure to estimate the true distribution, this one, out of the measure, this one is what we call unfolding, or unsmearing, or deconvolution. It depends on what field you are working in. So now let's try to define the different elements that are entering in the game. So in many practical cases, by determining the real PDF, f true, what we are doing actually is to determine the values of a histogram, which I will call mu, with m elements. And the values of mu are given by the total number of events from a given measurement, let's say, or realization, and the integral within the different bins of this PDF. Now, in our experiment, what we are doing is to measure with the estimator x and build a histogram of the obtained values. And this, we will be representing it by this vector n with big N elements. N and m don't need to be the same. Now, the expectation or the expected values of these n are, we call them nu. So nu are the expected values of the measured elements of the histogram. For example, if n are independent Poisson variables, each of them will be related, or will have a probability, which is a Poisson. We have again a Poisson of of the getting a value n when the expected value is nu, when the mean value is nu. It doesn't have to be like this, it's just an example. In any case, it's important to know the shape of this probability or likelihood in order to solve to apply unfolding methods based on maximum likelihood, or you can also use least squares, and then what you will be using is the covariance matrix. Providing one or the other is in many aspects is equivalent. For instance, for independent Poisson distributed, the same case as here, this is the covariance matrix. Now, migration matrix. The migration matrix relates the expected values, the true values mu with expected values, measured values nu. Okay? So this is just the way we compute the expected value of nu, starting from all the values of mu and related by this migration matrix. In this sense, this migration matrix is defined as the probability of observing or measuring an event in bin I when the true value of the variable we are measuring is in bin j. And this is represented by this expression here. We have this convolution of the resolution function that tells you how many of the events being in one bin will drift or spill over into the other. And here is separated the efficiency, because sometimes an event with a real value y will simply not be detected, and this is here separated. In our case, this is included in the effective area. Okay, so we are convoluting the PDF, the true PDF, in this way. And as you can see, the migration matrix in principle depends on the true PDF, and the true PDF is what we want to determine. So in principle, we should use the information we are trying to determine to solve the problem. What it is done is, because if you realize that if this epsilon and s are considered constant within a j bin, they can go outside, and then what is left here is the same as in the denominator, and it cancels out. So when can these two quantities be considered constant within a bin? When the bins are small. So that's why this migration matrix has to be done in sufficiently small bins in order to be as precise as possible. In any case, in this context, the migration matrix is supposed to be exactly known, whereas in principle we estimate it. We used our best estimate that can come from, in our case, from Monte Carlo simulations. In other experiments, it can come from the dedicated calibration runs. But it will always have an uncertainty, and we are just ignoring it, disregarding it. So this is how a typical migration matrix can look like. In this case, it is done by considering Gaussian estimators with no bias, and a sigma standard deviation of 2 in these units, which is the number of bins. Again, is constant along the whole range. And if you fixed a value of j, which means a real true value, for example, true energy, what you get is a one-dimensional Gaussian centered at y equal to j. And if you make the integral of this, or the sum over all the bins or of these elements in a column, the sum should be the efficiency. But the maximum should be 1, and if you get less, it's because some of the events are simply not detected. As I said, this is in our case taking into account in the effective area rather than in the migration matrix. It is. Now, we can also have a presence of a background in the measured distribution, and the backgrounds I will refer to them as beta of I being the measured bin. And then the equation relating the expectation values for the measurements and the true values we want to determine should be modified by adding to the expectation values of measured events this background that will be added to whatever signal we are measuring. Now these beta in principle are also random variables because they are determined from dedicated measurements or from simulation, and they will have uncertainties. Here we are assuming that they are unknown because the problem will, well, it gets more complicated otherwise, and it's somehow out of scope. Now, if you realize this expression here is just a system of n equations, so one equation per each value of I, n, with m unknowns. M are the possible, the number of mu events. And then, well, you have the usual situations where you can have an under-constrained system or over-constrained, or when in a case n equals to m, there is only one exact solution for the system of equations. Now, the point is that the exact solutions are of little or non-practical use, and we will see why immediately, and that is why this is an interesting problem to solve. And the main problem to solve this equation is that not only we don't know mu, but we also don't know nu. Okay, because what we know is n, and n can be used as estimators of nu, but when you do so, the solution you get has some problems. So this is a summary of the notation just to make it clear what we are talking about once again. So we have a vector of m values of mu, which are the histogram of expectation values of the true number of entries. And this is what we want to determine. N, the vector n, is the histogram of measured values, the data. Nu is the histogram of expectation values of the observed number of entries. So nu is the expectation value of n. Then we have efficiency, background, which mainly we won't use very much. The migration matrix and the covariance matrix, so that will be represented by V, that we need to use to solve this. So this is in the matrix vector notation, the previous equation. The equation we want to solve is this one. The vector nu is equal to the matrix R times vector mu plus vector beta. And the goal here is to find estimators for mu, which is the true histogram we want to build, to recover. Now, direct solution. Well, the direct solution, and I will concentrate in the case for practical purposes when n is equal to m and r is invertible. R is normally invertible for most probable practical cases, and this you can always impose by selecting your binning in your data. So now you can invert the previous equation, and then you get that mu is equal to the inverse of the migration matrix times nu minus beta. Now, as I said, beta we are assuming we know, but nu we don't know, and we can use the measurements n as estimators of nu, and then in this way we get estimators of mu. Okay, so this equation here we take estimators here, and for the ones of nu we take n, and this is a solution in principle for estimators of mu. Now, this solution is the one that we would also obtain, and it can be proven in a trivial way by maximizing the log likelihood function of the mu. And as I said, we need to know what is the PDF or the likelihood for the nu. In this expression here, and you know nu you can compute out of the mu using the migration matrix. Okay, so if you do so and solve and maximize this expression or this one, which are the same, then you get a solution, and the solution is this one, that the estimators for nu is equal to n. These estimators computed in this or this way, which are equivalent, they have some, statistically speaking, nice properties. Is that they have zero bias, and well, we can compute the covariance matrix in this way, multiplied by the inverse of the migration matrix at both sides, transposed in the right one. But let me show you with an example what happens when we use this solution. Now we're starting from this true distribution that we want to recover, and this migration matrix that I was showing before. Now in this plot is shown in solid the values of nu, so the expectation values of the measurements, and in the data points, one possible realization that you see has some statistical fluctuations with respect to the expectation values. Now, if we take the values of n and multiply them by the inverse of the migration matrix, what we get as estimator of mu is this thing here. Okay. So first note that the scale is completely different here. So here are the order of 5,000. Here are the order of 1,000 times more. And these error bars are the standard deviations of the estimators, computed because we know how to compute the whole covariance matrix of the estimators. Now let me insist that if you did the same, instead of using the data points here, you multiplied the histogram, the solid histogram, which is nu. You multiply it by the inverse of the migration matrix, you would recover exactly this by construction, okay? Because nu is just this histogram multiplied by the migration matrix, okay? So if you do the inverse operation, you must recover the result, and it happens. You can check it very easily in a practical situation. But as soon as you include the statistical fluctuations and you do the same operation, you get this kind of solution, which is statistically speaking is correct, and it has some, in principle, nice statistical properties. But as you can see, we cannot use for to provide a solution to our problem. So what do I mean by nice statistical properties? First, what I already said, that these estimators have zero bias, and the second one, well, no, this is the only one actually. Oh, well, it also provides the smallest possible variance for any choice of estimator with zero bias. So among all possible estimators of the mu with zero bias, this one provides the smallest variance. And you can see that it was very large, but it's the smallest possible one. And this is assured by the Rao-Kramer theorem that I will not try to describe here, but tells us precisely that. What is the minimum variance for a zero bias estimator? And you can check that the one provided by this estimator is precisely the one predicted by the Rao-Kramer, or the Kramer-Rao in some other text theorem. In other words, zero bias by using a zero bias estimator. So what is the solution? The solution for getting some practical result is to allow some controlled amount of bias so that the variance is reduced to an acceptable level. This is what we will try to do. And how do we do that? Is by introducing some prior knowledge of some property of the true distribution. And the most common one is smoothness. That means that the distribution cannot vary like crazy, but that the values of one being is not very different between codes from the previous being and the next one. There are several ways of imposing this smoothness, and this is what is called regularization, and we will see a couple of methods on how to do that. Yes. Questions so far? So first, before going to what is normally known as regularization, let me talk 10 minutes. Okay. Forward unfolding is a kind of regularization because we are imposing a knowledge on the function, on the distribution that you want to determine, which is the true PDF. And what you're imposing is that it has some particular shape, functional shape, with some parameters which are free, theta, I will call them. And then you can determine the values of theta by making a chi-square or least square minimization, which is this expression here, in which you minimize the differences between the computed mu as a function of theta. This you can compute because you know, once you determine theta, you know this f true, and mu is the integral of the f true within a being. Then you multiply it by the migration matrix to get nu, and then you compare the expectation value with the measurements, and then you can do a normal least square, okay? Or you can do also maximum likelihood, maximization of the likelihood function, which is completely equivalent to doing this. And as I said, this unfolding can be understood as a regularization, since we force the shape of the probability density function. And if you know an expression for your true PDF with some free parameters, then this provides the most robust solution for the problem. But for us, it's not useful in many practical cases. Well, this is just an example on how this works. You will be starting from the measurements in the dots here, and by imposing that the shape has to have this double Gaussian shape, the shape of the true PDF, you make the maximization, the minimization of the chi-square, or the maximization of the likelihood, and you would get back the initial results that are the ones in the histogram. Now, regularization. So we saw that the direct solution that we get by inversion of the migration matrix, what we get is the maximum likelihood solution. So this one, the one that maximizes this the likelihood, that has large variance and no bias. Now, how do we include an amount of a controlled amount of bias? Is to allow solutions that fulfill this condition, that the likelihood is larger than the maximum one minus a certain difference, and the amount of difference will be related to the amount of bias that you are allowing the estimator to have. So this delta log L measures the trade-off between the variance and the bias of the solution. And then to allow for additional bias, I mean to control it in a way we want, what we do is to add, to maximize not only the likelihood, as in this expression here, but the likelihood plus some other function that we call regularization function. And this some other function is normally a certain measure of the smoothness of the solution, or a measure of a certain property of the solution that we want to impose, no matter what it is. If we know something about it, we include a measure of that property in this function and add it to the log likelihood in order to maximize it. Now there is a relative weight between the two things, which is this parameter alpha, that tells us what you are giving more weight to, whether it is to the likelihood or whether it is to the regularization function. Now alpha is called the regularization parameter, and if is equal to 0, this term here is cancelled, so then you get the smoothest possible solution, but it doesn't take into account the values of n, because n is not entering here. This is only a function of the true parameters. It is entering here because the likelihood is the likelihood of mu given n. On the other way, if you go to the other extreme, alpha tending to infinity, then you are disregarding this part and you go back to the maximum likelihood solution, which has the problems that we have seen. And then selecting alpha somewhere in between infinity and 0, you will be actually adding one certain delta log L to this expression that we saw before. Now this S depends on the regularization method that we are using. There are many ways, and we will see a couple of them, and there are others used in magic. And yeah, there are also different possible ways to select the optimal value of alpha, and I will also mention a couple of them. And that's equivalent to select a value of delta log L. And the ones I show, at least they are based on the estimated variance and bias of the estimators of mu, and also on the variance of the bias. Now, let me remind you that these expressions that relate mu with mu are always true, okay? For the true values and for the estimated values. What is not true when you use regularization is that the estimators for mu are n, because this will get us back to the maximum likelihood solution. What it is normally done is to impose that the total number of estimated events, which is the sum of all the nus, is equal to the total number of events. Also, in order to keep the solutions close to this condition. It can be fixed or imposed by adding it to the likelihood. So a couple of regularization functions that are commonly used. First, Tikhonov. Tikhonov uses as smoothness measure the mean value of the square of some derivative of the true distribution. Okay, so the regularization function of the true distribution would be some derivative, some meaning that this k can be 1, 2, whatever, so it can be the first derivative, the second derivative, the third derivative, and then you square it. And this minus sign is because s, we want s to be maximized, and then this s is lower when it's more smooth. So just to make this go in the right direction, you put a sign, a minus sign. Now the most common choice is to get the second derivative here, and this is, I think, what we are using in Magic. So S would be in that case a measure of the average curvature of the function. You don't want the function to have a second derivative very large in any point. Another common regularization function is the maximum entropy that uses this expression. This is a measure of the entropy, meaning how many combinations of the data produces the same distribution. So for flat, you have maximum entropy, and when you have all the events accumulated in one single bin, you have minimum entropy, and everything in between. And you can find many more in the literature. Just wanted to provide a couple of examples. And now the choice of the regularization parameter. Well, this is a repetition of what I already said. The optimal, what we do is to compute the covariance matrix for the estimators of mu, whatever they are. There are methods standard methods to compute, starting from the regularization method and the covariance matrix for the measurements. We can compute the covariance matrix for the estimated mu's. We can also estimate the bias of these estimators, of the estimators of mu, and we can also estimate the variance of the biases. Okay, and that we call W. And now, based on these three quantities, okay, we can provide methods to determine which is the optimal value of alpha. So the first one would be the mean square error. So we multiply the variances, we sum the variances and the bias for a given bin, and we minimize this quantity. So we do that this mean squared errors, that is the sum of the variance and the bias, is the minimum for all the bins when you sum all the bins. Okay. You can do the same, but weighting it. You see here is the same quantity, but you weight it by the mean value of the estimator in order to have a weighted error rather than an absolute error. And there are other methods like making the biases and the standard deviations of the biases on average equal to 1. So you don't want to add a bias which is larger than the own variance of the bias. So in this case, you can set this condition. There's this other one which I don't want to enter because it uses some non-defined nomenclature here. It comes from old version of the transparency, but I leave it here for the record. And there are other criteria that you can use to select the optimal value of alpha. So now what will you do in practice is you choose an alpha, you select one of these methods, and then scans values of alpha until the condition is fulfilled, and this tells you what is the optimal value of alpha. So this is shown here for the 4 methods that have been explained. The figure shows the different parameters used to select alpha. Yes, this is as a function of delta log L, and delta log L is related to alpha. So for a given alpha, you have delta log L and vice versa, but it's more convenient to represent it because the minimum, well, the plots are somehow more compressed. But it's the same, you could compute it as a function of alpha. And then you have this mean squared error, which is the sum of the bias and the variance, and is this solid line here. So you see how this curve has a minimum, and for this minimum you read what is the delta log L, and this tells you what is the alpha, the optimal alpha. The same for the weighted mean squared error and the other 2 methods, which is when the value is equal to 1. So now this is the result. So in practice, what I have done here is compute the estimators by numerical maximization of the equation 5 that I showed before for different values of alpha, and for each of them I have computed what are the variance, the bias, and the variance of the bias for the estimator, and find what is the optimal alpha for each for several methods. Here I'm showing just one, and then here you see in green what was the original distribution from which I have constructed the expectation of the measurements, and from that realization of the measurement that is shown in this dotted histogram. And for the optimal values of, in this case I think is the mean squared error, what is the resulting estimated histogram in the dots. And this would show what is the variance, what is the bias for the estimator, for each one of the estimator. This is the bias, the central position, and the error bar here is the variance of the bias. Here, the error bars are the variance of the estimator in themselves. But as usual, the error bars here are not uncorrelated anymore. So the variance, which is the diagonal of the covariance matrix, is not enough in order to perform a fit, for example. You need the full matrix, and the full matrix can be computed very straightforward using the migration matrix and the initial covariance matrix. And that's it. Questions?
You show really nicely how a detailed measurement like bonds or so can be reconstructed using unfolding. How big is the influence on our spectrum, which is extremely flat and has no details at all?
I don't understand the question.
Why do we do unfolding for our spectrum?
Why?
Yeah.
Because
We don't
otherwise
need to reconstruct details.
you don't what? Say it again.
We don't need to reconstruct details because we don't have them.
No, but there is a detail which is normally changed when you do unfolding with respect to not doing it, which is for a power law spectrum, you will get a completely different slope.
Is it? You don't
Yes.
show the... I haven't done it. I mean, I don't know.
No, I don't show it here because I wanted to do a general thing, but this from our practice, our experience, I can tell.
There are some features, like the cutoffs. In a cutoff, you really can have some important effect, because if there is a cutoff, for instance, with the flux falls very pass, you will have a lot of spillover from events which have actual energy below the cutoff that are reconstructed above the cutoff. So if you don't apply some kind of voltage, you will reconstruct the cutoff which is much less sharp than the actual one. Then, at least for that case, you need some kind of voltage because the energy resolution is like 15%, even at the best situation. And there are things, at least these cutoffs that produce sharper features. I agree, we don't have line, we don't have many features, but there are some.
But our energy density are large compared to our energy resolution.
Well, it depends. The size of the energy beams is determined by the intensity of your signal. If your signal is strong, then you can have a beam which is comparable to the energy resolution. It doesn't make sense to make it much smaller, but comparable. And still in those beams, this spillover effect can be very, very relevant. So you need maybe, I mean, I'm not very fond of full-on foreground. I think it's a bit complicated method, but you have to do some kind of correction.
Another thing is that most of the low energies you have this pile-up. Those come not done unfolding because a number of events to low energy is dropping in some point, but there is some migration.
Yeah, in this case it's not a cutoff, but a very simply rising efficiency. Yeah. Right. So low energies you will tend to reconstruct events with quite long energy with the bias because of the selection effect on the trigger. And then if you don't correct for that, you will have nothing spectrum.
So we correct for that by dividing by the effective area?
No, because effective area in principle, well, I will talk about that. The effective area in principle, the true one is versus true energy. If you want to correct for that, when you divide by the effective area, you have to calculate a kind of modified effective area that takes into account this energy resolution and this energy bias. So it's you cannot ignore it. And much more so when we have only one telescope in which the resolution was worse. Now we are closer to the situation in which we could be doing, in some situations, ignoring it. It's not like that.